the last lecture, I had started discussing the properties of a p-ion diode, which is used for detection of radiation. The structure I had shown is as follows. There is a relatively wide I layer, intrinsic layer, in the middle, whereas at the top there is a thin P layer, and at the bottom there is a thin N layer. The widths are relatively small of the P and N layers. They're WP and WN. The idea of this PIN structure as opposed to a PN structure is to have the I layer width wide enough such that it can absorb most of the radiation. If we have radiation of intensity P opt incident on the top, and R is the reflection coefficient, then obviously R into P opt is reflected. 1 minus R into P opt is the power that is entering the semiconductor, and it decays as e to the power minus alpha x, where alpha is the absorption coefficient, alpha is a function of wavelength. So in order to get high quantum efficiency and high response, this I layer width is tailored such that it is comparable with 1 by alpha. 1 by alpha is the depth at which the intensity drops to 1 by E of its value. So one can choose the width W in comparison with 1 by alpha at a particular wavelength. From the electrical point of view, the advantage of such a device is that if the I layer is relatively lowly doped, it need not be intrinsic layer as such. It could be a nu or a pi layer, relatively lightly doped semiconductor region. Then the field appears mainly across the I layer. So there's a high electric field across this layer, so that if electrons and holes are created, they immediately separate due to the high electric field, and they are collected, the holes going to the P region and the electrons going to the N region. And the applied voltage QVR being several times the band gap of the semiconductor. It could be typically something like 10 to 15 volts. You notice that the electric field profile that I've drawn this time, the field is constant. The field is the slope of this diagram, energy versus distance diagram. So the field is constant across this, and there's only a very weak field in the heavily doped N and P regions. So the carriers that are created in the N and the P regions, they move due to diffusion. This must be within the diffusion length of holes in the N-type region, and here the electrons, this must be within the diffusion length Ln of the electrons in the P-type region. So as I've discussed last time, we find that the total current has a drift component due to the intrinsic layer plus a diffusion component due to the carriers created in the top and bottom junctions, and we find that the quantum efficiency eta was J dot by Q. This is the number of electron hole pairs created over P opt by A H nu. A is the area. So this is the number of electron hole pairs over the number of incident photons. There is a related parameter called responsivity, which I've talked about before. Responsivity is just IPH over P incident, and this is eta Q by H nu, and this is just eta lambda in microns. If you write this as HC by lambda, then you have the old formula. So the responsivity in amperes per watt of a photodetector, the output response is in amperes, the input is in watts, is just eta lambda over 1.24. So where eta is defined here. So for example, if lambda is 1.24, then R is equal to eta. Okay? And if lambda is longer, for example, if lambda is, say, 5 microns, okay, so this factor will be something like 4 into eta. So the responsivity can be much, whereas the quantum efficiency is limited to maximum of 100%, the responsivity can be more, can be, suppose the quantum efficiency is suppose we take lambda is, say, 5 microns or 4.8 microns, say eta is 0.8, the responsivity is 0.8 to 4.8 by 1.24, 3.2 amperes per watt. Notice that responsivity is proportional to lambda. Okay, why is that? Because for a given P opt, okay, the number of photons is obviously inversely proportional to lambda, right? Because this is n into h nu, okay? H nu is hc by lambda, okay? So for a given P opt, obviously it takes many more photons of lower energy, okay? N is equal to P opt okay, n is equal to n opt P lambda by hc. Okay, so this is wrong. And for a given P opt, right? At longer wavelengths you have to have larger number of photons, and therefore this responsivity is proportional to lambda. Okay, last time what I had calculated was that for a PIN diode, where R is the reflection coefficient, W is the width of the eye layer, alpha is the absorption coefficient at a given wavelength, and LP is the minority carrier diffusion length of holes in the N-type region. So we want, for eta tending to 1, we want R to go to 0, and we want alpha W to be large. So alpha W should be much larger than 1, or W should be much larger than 1 by alpha. Okay, so this is one. So that all the light is absorbed in the intrinsic region. If you look at the denominator does not play a major role, but however, if we want the denominator to be large, such that this term is small, then obviously we want the condition that alpha LP should be large, or LP should be large. Okay, LP should be obviously if LP is large, the diffusion current is, if LP is large, we have this diffusion current due to holes, whatever. It's a small fraction, but that will be collected. It will, if it once diffuses into the high field region, then it will be collected. Okay. This relation is quite important in the sense that it gives us a method of calculating LP. Let me just go into this in a little detail, because minority carrier diffusion lengths are things that are important in photodetectors and solar cells, etc. Suppose we take the same, suppose we neglect R. R is, say, it's something that is constant as a function of lambda. Suppose we take W is 0. That means at the surface. Then this relation becomes eta is equal to 1 minus 1 over 1 plus alpha LP. Okay. We have taken W is equal to 0, so e to the power minus alpha W is just 1. And this we can easily rewrite as okay, and so we can rewrite this as 1 by eta is equal to 1 plus 1 over alpha LP, where eta is a function of lambda. So at the surface, suppose we have okay, the light is in general, the intensity goes as e to the power minus alpha x, and I'm putting this x is equal to 0. Okay, I'm putting this x is equal to 0. This is strictly speaking valid not for a PI endowed, but for any solar cell. Okay, where at putting x is equal to 0. Okay, so if you measure the quantum efficiency, this is a function of current. Okay, quantum efficiency I've already calculated, and as a function of alpha, what do we find? We find that against 1 by alpha, that means we measure the spectral response. We measure the spectral response of a solar cell, which could be something like this as a function of lambda. Okay, and we find we have okay, this is the spectral response of a solar cell. Okay, so and alpha is what? Alpha we know goes something like Okay, maybe alpha goes something like that, which is known, right? So we plot this part of the spectrum, okay, where alpha is increasing slightly, okay. So 1 by alpha is decreasing. This is the near the band edge, okay, and the quantum efficiency is increasing. So if we plot this as 1 by eta is 1 by alpha, we'll get plots like this, and the slope of this is 1 by LP. Okay. At relatively low values of, we can approximate this, at low values of alpha and LP, this is almost equal to 1 by LP. Okay. So we are plotting 1 by eta against 1 by alpha, and the slope is 1 by LP. So we can get, for example, if the LP is small, we will get a variation like that. And if, for example, the surface is passivated, okay, then we'll get a variation like that. Okay, so this is a standard method of determining LP from the spectral response of a solar cell. Okay, let me get into, we have talked about the quantum efficiency, into the speed of response, into the frequency response of a p-ion diode. This depends upon the transit time of carriers. Mainly in the I region, because this is the widest region. And so, as I've mentioned before, if the I region is made, if W, the width of the I region, is made very large, if W is made very large compared with alpha, then you have high eta, but transit time is high, so it is a slow device. Okay, and obviously, if it is not as much, then you have a fast device. So, if eta is, for example, less than 1 by alpha, then we have small eta, but it's a fast device. So we want to calculate what exactly is the F3 dB. Where does the response of a p-ion diode decrease? In order to do that, we have to look at the response of a p-ion diode. Suppose we can neglect the initial P width is very small. Suppose this is the I layer width. We have incident light, which is modulated phi 1 e to the power j omega t, modulated at frequency omega, and due to this we have a current due to carriers, and there is also an electric field. The electric field applied across the device is considered to be high enough to deplete the I layer. So we assume that the carriers move with saturation velocity V sat in centimeters per second. Okay. So again, we have two components of current. The current has one is the conduction due to the carriers, plus there is a displacement current. We have seen that if that is the photon flux, then the conduction component of current, X, is equal to Q phi 1. The AC component of flux, e to the power j omega t minus X by Vs, where, or Vsat, where Vsat is the saturation velocity of carriers. Now we want to calculate what the displacement current is. From Maxwell's equations, we know that the divergence J of total current is equal to 0, and J dot is equal to 1 by W, 0 to W, J conduction plus, and the displacement current is just delta E, delta T, the variation of electric field with time, and this is the dielectric constant, into dx. So this is the displacement current density. So substituting, we find that where V is the applied voltage plus Q phi 1 minus j omega tr, where tr is the transit time, into e to the power j omega t, where tr is nothing but W by Vs. That is the transit time of carriers. And V is the applied voltage plus the built-in potential VBI. Now we can take the condition where V is equal to 0, or it's relatively small, so the short circuit current in that case, JSC, is Q phi 1 minus e to the power j omega tr over j omega tr e to the power at the modulation frequency. So you see that this short circuit current, as a function of omega, all the other terms being constant, depends upon this magnitude of over j omega tr. And if you plot this as a function of omega tr, over j omega tr, we find that it decreases quite rapidly, goes to 0 at a value of omega tr little less than 6, and it again at 12 I think there should be a minus sign here everywhere, right? So what does it show? That as TR is a function of the material, okay, it's W. TR is W, not to confuse W with omega, okay? So for a given device, W is fixed, Vs is material dependent. As omega increases, what happens? The response decreases, goes to 0, and then you have subsidiary maximum. Okay, so JSC, if this is 6, so even at 1, it reduces. So JSC decreases rapidly as omega TR is greater than 1. And from that graph, we can see that omega TR is equal to 2.4. JSC is JSC max by root 2. So this is the 3 dB point. Okay. So we have the condition that F3 dB is equal to 2.4 by 2 pi TR. This is 1 by root 2, 3 dB. So if you omega is 2 pi F, okay, so we take this is 2.4 over 2 pi TR, okay. So this is equal to 0.4 Vs by W. And if W is equal to almost 1 by alpha, then we have F3 dB is equal to 0.4 alpha into Vs. So this is an important relation that and this also is an important relation, okay, it's a more general relation, that as W increases, okay, F3 dB decreases. Okay. But quantum efficiency increases, but F3 dB. Why is that? Because after all, the carriers take a certain time. When you have a modulated signal, the carriers take a certain time to move through the I layer, and as the frequency becomes very large, then the carriers are out of phase. When the signal is the maximum, the carriers, become out of phase. So in this same graph, we can plot the phase shift. The phase shift goes so the phase is also a periodic function of omega TR, and in this case, under this condition, the phase shift is 2 pi by 5. Okay, so this is 360 by 5. That's about 72 degrees. So there's quite a lot of phase shift under these conditions. So we come to the conclusion that F3 dB is inversely proportional to W, and however, we want if you want enough light absorption, so a reasonable compromise to get high eta as well as a reasonable 3 dB is that you make W something like 1 by alpha to about 2 by alpha. Okay. So this will give you reasonably high eta and reasonably high F3 dB. If you want to, as I've said before, if you make W too large, then F3 dB goes down, quantum efficiency goes up, and vice versa. For silicon p-ion diodes, there's a nice plot. You can plot eta, okay, which is maximum 100%, okay, and this is F3 dB in gigahertz, going from, okay, now if you for say a given value of okay, let me just plot this. Frequency going from 0.1 to about say 10 gigahertz, and on this side we have the W, which goes from 10 microns to 100 microns to 1000 microns. And what are these graphs? These are for different lambdas. Lambdas 0.6328, helium neon line, 0.8, 0.9, 0.95, 1, and 1.06 microns. So what does this graph tell us? That for a given p-ion diode, if we have, say, lambda at 0.6328, then alpha is very large. Okay, if alpha is very large for a given width of the W of the intrinsic layer, the quantum efficiency remains large, okay, up to a high frequency, and the 3 dB the quantum efficiency remains high, and the frequency response is also high. Okay. Now suppose you take longer wavelengths. Okay, longer wavelengths. At 1 micron, the absorption alpha is much smaller. Okay, so if alpha is much smaller, quantum efficiency comes down. Okay, and so if the quantum efficiency comes down, we find that the response is is like this. The F3 dB is then for a given value of W, okay, it is somewhere here, whereas for a same wavelength, okay, same wavelength, if you have a thinner device, okay, the F3 dB is much larger, okay, but the quantum efficiency is smaller. Okay, if you follow one of these lines, if W is only 10 microns, F3 dB is much larger, but the quantum efficiency is smaller. Here you have quantum efficiency larger, but F3 dB is smaller. Okay, and here 1.06 microns is ND-YAG laser, where optical absorption is very small. Okay, so therefore you don't get a very high quantum efficiency at all here. This is a typical silicon p-ion diode. Suppose we take another p-ion diode, which is very important in suppose we want to, you have a laser, gallium arsenide laser, lambda is say 0.83 microns. Okay, and we can see that in this 0.8 microns, okay, so 0.8 microns, F3 dB is fairly large, okay, and eta is also fairly large. And obviously, what can you use with this? You can use a silicon detector, silicon p-ion, and it will give you reasonable response. Why? Because the silicon band gap is 1.1 eV. Okay, so this is one case. But suppose we want, for fiber optic applications, we have lambda is 1.3 or 1.55 microns. Okay, this corresponds to a band gap of about 0.9, and this is of the order of about what? About 0.8 eV. Okay, obviously silicon detector will not be responsive to this wavelength. So what do you use? We use a in-gas detector. Whose band gap is 0.75 eV, okay, and less than that. Alternative is, so we can use a germanium detector, which EG is equal to about 0.67 eV. Which do we choose? We know that in-gas is a direct gap semiconductor and germanium is an indirect gap semiconductor. So the absorption width for in-gas will be smaller, and if we draw a similar graph as for the silicon p-ion diode, we find that here fiber optics, the frequency of modulation is very high. F3 dB is 10 to 90 gigahertz, and if you plot eta over 1 minus r, this is 100. For in-gas, we get a this is in-gas, IN 0.53, gallium 0.47, which is lattice match to indium phosphide. Whereas for a germanium detector, we find that the quantum efficiency is lower right through. This is the response of germanium. Both, this is at lambda is 1.55 microns, and we are assuming Vs is 10 to the power 7 per second, and we can draw on the top the depletion width goes from 0.5 microns to 5 microns. So, say for 0.5 micron depletion width in gas, we have this quantum efficiency and this value of F3 dB. If you want this same value of quantum efficiency, okay, for germanium, then we need much higher depletion width, right? But on the other hand, we get the same quantum efficiency here, but then the F3 dB is less, okay? So that is because germanium is an indirect gap semiconductor, so alpha is lower, at a particular wavelength alpha is lower, and so if you have to compensate that having a higher value of W, if you have a higher value of W, then F3 dB comes down. An alternative is to have heterojunction photodiodes, which I'll just mention. Typically, this uses a heterojunction between indium gallium arsenide, because it is in any case grown on indium phosphide, okay? And the structure is something like this. We have a P plus in-gas layer made by zinc diffusion. Then a P layer, and then N plus in indium phosphide, which is lattice matched. We have so the junction is here, and we have SiO2 passivation, etc. So this is the junction. And the light, we have metal. This is an old circular annular metallic contact, and the light comes enters indium phosphide. Indium phosphide is completely transparent at 1.3 or 1.5 microns. Light enters here, and notice here this P is substituting for the I. Okay, it's a p-ion diode, but you're not getting an intrinsic layer, but it's a P layer, and we have another metal contact here. Okay, the reason this is a MESA diode, and the reason why one uses this heterojunction photodiode is that you have, since this band gap is larger for indium phosphide, we have advantage of heterojunction. Since we have higher Eg, okay, we have lower dark current and higher breakdown voltage, VBD. So I'll come to a discussion of these heterojunction photodiodes in detail later. I just want to show you a simple silicon p-ion diode, and this is a fairly large area silicon p-ion diode, which, as you see, has a metallic annular electrode. Okay, that is to reduce the surface leakage and the dark current around the junction, and it has a anti-reflection coating. That's why it looks black, dark, and it has one ground terminal, and the central portion is the active area. It's a planar structure with the other contact taken from the bottom of the device. This is a fairly large area device. You can see the diameter is of the order of 2 to 3 millimeters. If you are interested in optical fiber type of detection, then you have very small devices of this type, which has a lens which can collect light and focus it onto the active area. One of the great advantages of small devices is, of course, the area being smaller, the capacitance is smaller. Okay, so the response speed is not only limited by the transit time, but it's also limited by the capacitance. So for an optical fiber detector, the area is typically, the central area is just larger than the inner diameter of the fiber. It could be 20 or 30 microns. And the capacitance in that case is of the order of less than picofarads. Okay. In order to reduce the RC time constant, the area is made very small, and you have, okay, you compare the two PIN diodes. These are both silicon PIN diodes, which have very good response in the gallium arsenide wavelength frequency. So they're very useful in detection up to about 1 micron wavelengths.